Do you charge your phone once a day or even twice a day? What if I told you that a team at Peking University has just published a breakthrough that could extend your phone's battery life from 1 day to 3 to 5 days, maybe even a full week on a single charge? This isn't a concept. It's not a PowerPoint fantasy. It's a real technological breakthrough just published in Science Advances. On the 14th of February 2026, the team, led by Professor Chucheng Guang and academician Lianmao Peng from the School of Electronics at Peking University, created the world's lowest power ferroelectric transistor. The gate length is just 1 nanometer. The operating voltage is only 0.6 volts. And the energy consumption is an order of magnitude lower than the current international best. Today, let's break it down. What makes this technology so powerful? And how could it dramatically boost your phone's battery life? First, we need to understand one thing. What exactly is a transistor? Imagine the faucet in your home. Turn it on, water flows. Turn it off, water stops. Inside your phone's chip, there are tens of billions of tiny electronic faucets. They switch on and off billions of times per second to perform calculations. Scrolling social media, watching videos, playing games, running AI. All of it depends on these microscopic switches working non-stop. But traditional transistors have 3 fatal flaws. First, they require relatively high voltage to switch. They need effort. Second, they don't shut off completely. They leak electricity even in standby mode. Third, they forget everything when power is cut. They must stay powered to maintain state. That's why your phone loses battery even when you're not using it. That's why it heats up when gaming. Billions of tiny faucets are leaking and working inefficiently. The Peking University team's nanogate ferroelectric transistor is like upgrading every faucet in your chip to a precision, self-locking, ultra-efficient smart valve. Let me explain with 3 simple analogies. First, it opens with just a gentle tap, ultra-low voltage operation. Instead of forcing a stiff faucet open, the team engineered a 1 nanometer precision gate that concentrates the electric field. This field enhancement effect allows switching at only 0.6 volts. Second, when it's off, it locks completely zero leakage. Conventional transistors still drip electricity when turned off. Ferroelectric transistors have a built-in self-locking structure. On means fully on. Off means completely sealed. No leakage. That means when your phone sits overnight, the battery barely moves. Third, it remembers even without power. Traditional transistors are like goldfish. They must stay powered to remember whether they're on or off. Ferroelectric transistors are non-volatile. Even when power is cut, they retain their state. No continuous power required. Instant resume. In one sentence, traditional transistors are leaky, power-hungry faucets. Ferroelectric transistors are precision, self-locking, zero-leakage smart valves. That's how power consumption can drop by 85 to 90%. Now here's the key physics principle. Power is proportional to voltage squared. P is proportional to V squared. Even a small drop in voltage leads to a dramatic drop in power. And this is where things get interesting. Let's take the iPhone 16 Pro Max as an example. It has a 4,441 milliamp hours battery. Let's see what happens if this technology replaces today's transistors across major components. SoC light usage, like messaging or browsing. Current voltage 0.68 to 0.85 volts. Power 800 to 1,200 milliwatts. With ferroelectric transistors, voltage 0.6 volts. Power 250 to 400 milliwatts. That's a 65 to 75% reduction. Under heavy gaming load, current power 6 to 8 watts. With the new transistors, 2 to 2.8 watts. Peak power is cut nearly in half. LPDDR5X memory. Original power 300 to 500 milliwatts. With the new technology, 80 to 150 milliwatts. Plus, because it's non-volatile, no constant refresh is required. NVMe flash storage. Write voltage drops from up to 3.3 volts down to 0.6 volts. Power reduction, 85 to 90%. Standby leakage in storage, from 20 to 40 milliwatts, down to about 0.5 to 1 milliwatt. That's up to 98% reduction. 5G baseband and RF modules. Power drops by roughly 60 to 70%, especially helpful in weak signal conditions. Let's look at the big picture. Average daily use. Power drops from around 4.2 watts to roughly 0.8 to 1.2 watts. Battery life extends from 1 day to 3 to 5 days. Heavy use scenarios, from 6 hours to 20 to 25 hours. Pure standby, from 10 days to potentially 40 to 60 days. OLED display power doesn't change, that's a separate technology. But because everything else becomes more efficient, overall battery life still multiplies. Now, here's the most practical part. This breakthrough is fully compatible with standard CMOS manufacturing processes. No new factories, no new production lines, no exotic equipment. Existing fabs, whether using FinFET or GAA processes, only need to add a ferroelectric material deposition step. That dramatically lowers the barrier to commercialization. The team has already secured 3 core Chinese patents, covering device design, process integration, and system architecture. They are collaborating with major domestic foundries to transition from lab prototypes to mass production processes. Once validated, chip designers can license the technology and integrate it into next-generation processors without redesigning entire systems. For smartphone brands, it could mean simply switching to a new chip and instantly doubling battery life. And the impact goes far beyond phones. Wearables. Smartwatches lasting 2 to 3 weeks. AR glasses with 50% smaller batteries. Medical devices. Skin patches operating for weeks without replacement. Robotics and edge AI. Lower power. Higher local AI capability. Reduced cloud dependence. Data centers. Single chip power reduced by 70 to 90%, cooling costs drop dramatically. IoT networks. Sensors powered by ambient energy harvesting alone. Automotive electronics. Lower computing power consumption extends EV range. More capable autonomous driving with lower latency. Let's talk about the team behind this breakthrough. Professor Chucheng Guang focuses on post-Moore semiconductor technologies, pushing low-dimensional devices toward theoretical performance limits. Academician Lian Maopeng, member of the Chinese Academy of Sciences, leads the broader research direction. This is not an overnight success. In 2023, they published ballistic 2D indium selenide transistors surpassing silicon speed limits in Nature Materials. In 2024, they reported integrated 2D semiconductor processes in Nature Electronics. In 2025, they demonstrated ultra-low-powered 2D gate all-around transistors. And now, in 2026, in Science Advances, they've pushed power consumption to a new global minimum with nanogate ferroelectric transistors. From 2D materials to ferroelectric memory, from device physics to system integration, they've built a complete post-Moore technology roadmap. So let's return to the original question. Is 5-day battery life realistic? The technology is ready. Now it's a matter of industrialization. Imagine traveling for a week without bringing a charger. Outdoor adventures powered for days. A smartwatch you charge once a month. A phone so efficient you forget about charging altogether. That's the future promised by 1-nanometer nanogate ferroelectric transistors pioneered by the team at Peking University.